Alright, I basically cobbled together, a variant of this circuit here. Um, and what it's supposed to be is a circuit that, is makes the JFETs not so capricious. And, there's some evidence of that. Now, this is the exact version of it I pretty much built. Ignore this. This is just so I can try to characterize FETs on files tab, which is not as straightforward as it should be. But the exact components I used, are here. Okay, so again, I can't put that there because it causes this thing to freak out. So that's why I take it off. But this is actually just a capacitor I put in parallel with this, so I can try to improve the frequency response of it. And it did. I mean, it actually increased the bandwidth of it a little bit. But we'll get to some of the interesting behavior of that here in a minute. But basically, this is a constant current source of sorts. I mean, it's a transistor, set up as a voltage follower current source. So I mean, it's somewhat stable, not as good as a stiff constant current source like a or current sink like a current mirror or something like that. But anyway, it feeds the JFET, and basically we got our drain resistor up here, and this sets the current down here, with this resistor here. It's coming from ground going to the base, the 5-volt supply, so it's basically kind of directly program the current source here. Although because of the early effect and all that, there'll be some variation in currents. Like I said, it's not stiff, but it's stiff enough, I guess, to produce usable results. But of course, since that same current that's being sunk into this current sink, is also flowing through this resistor. Well, the larger this current, the larger the voltage drop across this resistor. So in effect, it sort of squeezes the JFET on either side, forcing it into a certain current, right? And it'll put whatever voltage drop necessary across it to actually bias the gate properly, to achieve that same current. So it forces the FET to operate at that current. So, and again, in a previous video, I speculated that, well, even if that worked, the transconductance would probably be different from transistor to transistor. And there's some evidence I've got to support that, but overall it's surprisingly stable even on gain. And you'll see that here in a second. And here's the actual circuit. You see I use some electrolytics, for, the 220s, and then some film caps, for the 1 microfarad capacitors you see there. And everything else is, pretty straightforward. So, you got your 2N2222 transistor there, and then our test FET. So, which right now, I think I have a J211 in there, if I'm not mistaken, because I tested 2 different MFP 102s and 2 J111s, which, if you remember from previous videos, are rather high current FETs that are hard to use, and then 1 MPF 102. So, and here's kind of my rig up, basically, got the blue probe, for input, as I often do, our function generator input, the red alligator clip, and then the red probe, as our output. So, without further ado, let's see. Well, let me go pull these up here, and I just went ahead and just did them as a I ran the whole set so I don't have to bore you with it. Um, so you can see um, the results, of running the network analysis on it. I ran it out to 2 megahertz because these things don't seem to go much further than that. I did run one down to 10 hertz and it was still almost unflinching. I mean, it was, that's a great thing about these JFETs. They have such high input impedance and everything. So you stick a, you can stick a pretty small input cap into it, so you can get some good frequency response out of it because of that. At least on the input. But yeah, you see here, we're talking about a gain of about 6.5. Clear across the board on this this is J111 here that I tested, and okay, it's about 6.5, and its bandwidth, is falling off to probably right here is probably about the 3 decibel point. It's around 1 megahertz bandwidth, which isn't half bad. And going to the next one, this is the second J111 I tested. So you can see it's, gain's pretty much exactly the same practically, and the bandwidth is, about almost exactly the same. And then here we're seeing a J211, which is what I got in there right now, and again its gain is 6.5. Of course, its bandwidth, starts crapping out at about, probably 500 megahertz or so, or 500 kilohertz or so. So it's not got the bandwidth of the last ones. And then here, you see, again, gain 6.5, and this is on a MFP 102 or MPF 102. So, and it, it's gained about similar to the last one, actually closing in on half a megahertz. And then here is a second MPF 102 I tested. So, because I tested 2 of these, 2 J11s and 111s, and then J211. So again, pretty similar performance, so same kind of gain. Now I did also, you notice the test, I ran it at half a volt, 500 millivolts, so it's uniform gain here, but let's see what it runs at a lower signal input level. Okay, so we'll start again here, okay, and this is the J111 1. Alright, okay, so at a lower gain, it's like almost 12 now, at a lower input signal. So, and it's not got quite the bandwidth, interestingly enough, for smaller signal. So that was a surprise a little bit, higher gain, but lower bandwidth. But, you expect lower bandwidth for higher gain, but, it's bizarre to see higher gain for a smaller signal a little bit. But the absolute voltage swing isn't going to be as great. So, yeah, I guess tit for tat. What the fuck? Okay. Wait, hold on a minute. I'm gonna close these down. Something fucking Windowsy just happened. Yeah, so this is the first J11, at 100 millivolts. What's this doing in here? Okay, anyway, there's a 50 millivolt J211, and that's running a gain of about 11. Yeah, that really actually shouldn't be in this folder, but here is J211 at 100 millivolts like it's supposed to be, and its gain's like 11 or so, so and then here is an MPF 102 number 2, you know, its gain's coming about 9.5, you know, at 100 millivolts, and you know, bandwidth down to 100 kilohertz. And then our first MPF 102 at 100 millivolts, so you can see similar performance. It's a little under 9. So again, the gain's not quite consistent anymore as the signals get smaller, interestingly enough. And incidentally, one of the reasons the big reason I ran this thing, you know, at the voltage I'm running it at, you know, 20 volts, is because of the J111s. At first I was going to run this thing only at 15 volts on that higher voltage side, but the J111s just weren't working, and they're producing a gain like 1.5 or something. And I realized it's probably because of the pinch-off voltage range is higher on a J111 than it is these other FETs. So these other FETs are probably 4 to 6 volts, something like that. Whereas that's, you know, probably 9 or 10 volts. So I think it was just running at the constant current source was running at it was squeezing it too hard, basically. There wasn't enough wiggle room for the FET anymore. So that's why I had to up it another 5 volts. But let's look at, let me go ahead and close this. And let's look at some signals now, and this is again the 211 that we have going on here, and I'm putting a square wave through it. You know, see, a sine wave, you know, looks fine, but you know, the square wave is very interesting. You know, it's rounded, you know, like that. And you can see the maximum swing on this thing is actually like 13 volts or so. So better camera of some kind. But at any rate, you know, at 13 volts or so is the maximum swing. But you can see this, you know, curve here. It's like a capacitance. But like I said, you know, you see how when I adjust the input signal, see how it's staggering on the bottom? That suggests to me it's a constant current source issue, you know, and that reminds me of a constant current source sort of trying to catch up with it. So not quite sure, you know, if that's responsible for it. What's interesting though is that, you know, if I go changing the frequencies, you know, that curve shape stays pretty much the same. So it's very strictly, you know, a transition, you know, a slew rate issue. You know, it's a you know, this thing seems to have kind of limits on that. You know, it's a fast rise pulse, and it really can't keep up with it too well. So, you know, so it's like I said, that's what I'm inputting into it right now. But like I said, as I reduce it, you know, it starts to become more and more square wave like. But yeah, I mean, no matter how long or short I make it, you'll start shark finning at some point. But you know, you stretch it out, you still see that same exact slope on there. So, you know, it looks like a capacitive effect. So, just not quite sure, you know, what the cause is. But like I said, you know, you go to sine waves, you know, it's you can see the attenuation, especially at 3 megahertz or so, like we're at right now. So, God, I hate this camera, man. I don't hate it as bad as some of the others, but you know, even this is, you know, giving us a gain of 5 here at 600 kilohertz, and you know, it's dropping down to 1.7 at 2.5 megahertz or so. So, you know, it's just some interesting anomalies. I can't explain, you know, some everything that's going on here, but it's certainly an interesting result, though. You know, like I said, if you're generally trying to amplify sine waves, you know, you're in pretty good shape. If we go down low enough here on frequency, you know, like 20 kilohertz or something like that, you know, we start to get, you know, fairly decent square waves. You know, 7 volt peak to peak, for crying out loud. So, you know, our gain is 10 right now, and that's for a 320 millivolt input signal. So, you know, with which we could go higher, you know, That's its like peak amplitude basically. You see those delays, see that bounce, that strikes me as like a delay in the constant current source or something, curiously enough, but that's supposed to be a bias effect only, so well, I think that's a capacitor charging, and maybe I used too big of one. Hazen had a similar circuit in his book, right down here. But it was for a single supply circuit, but I decided to basically build one more like Malvino because this is a little more complicated, so I wanted to keep it as simple as possible. So yeah, he's using 100 microfarad on his bypass cap. So of course Malvino doesn't have one. He hardly explains anything about it, but Hazen doesn't explain anything either. So I'm saying I have very little information to go on when it comes to these sorts of circuits. So it's this is almost all you see on Malvino. He hardly discusses them at all. In fact, one thing I like about Hazen more, for sure, the Malvino. The Malvino has some interesting stuff in there that Hazen doesn't cover. One of the interesting things I like about Hazen better is that Hazen, doesn't just tell you how to analyze the circuit. It tells you, a lot about design. Okay, so especially on bipolar transistors. That's why I say, it's a really good book for bipolar transistors. Even though you will learn a few additional things in Malvino, but because it is a 10-year newer book, and that was just the first edition. But the fact of the matter is that he does cover design quite a bit. So that's a big part of the exercises in his book in a lot of cases, especially bipolar transistors. But here he didn't cover any of that shit at all. So it was just like strictly for technicians or something. So anyway, but still, it was an interesting circuit. I'm actually pretty surprised at the results. So I sort of stand corrected when I said that FETs are so capricious they're difficult to use. But I'm sure you'd have occasions where this would be difficult to use. Either the split supply version, because you do still need a fairly decent sized voltage to make some of these work, and I assume you still maintain the high input impedance. But I don't know. It's going to depend on your own particular design paradigm, but I haven't really seen this used that often. So, there must be some gotchas to it, and maybe this little shark finning and all that. Maybe that's part of it. I don't know. But boy, that's bizarre. How that behaves. It's just so interesting. That correction. So it's like a delayed response. It's very curious. But at any rate, it's a pretty neat little circuit, though. It was a worthwhile little build. So, anyway, cheers.